Alrighty, lads and ladies, welcome back to Calc 2. Today we are charging bravely forward in the land of convergence tests. Last week we learned the comparison tests, which are a big deal. They're kind of the most powerful tests we're going to learn in a very real sense. There are lots of problems we can tackle with those comparison tests that we really can't tackle any other way. Today I'm going to start sort of broadening our horizons to talk about other series. Namely series where the terms are not necessarily all positive. We talked a little bit last time at the end of class about how series where the terms are not all positive can be especially strange. And while that might have seemed a little bit scary, today I'm going to show you the other side of that coin, which is that series where the terms are not all positive actually have a much easier time converging. So there's an up and a down to this stuff. Let me get my shit fixed up here so it's not in the way. We can get moving. All right. If we get interrupted, I'm sorry. I do have some people taking tests at the testing center right now. I've gotten some phone calls and stuff like that. So if I have to pause for a second, I do apologize, but gotta make sure that everybody's doing okay. Here we go. Oh, did I ever tell you guys where this background comes from? Pause for just a second here. Did we ever talk about this? This is pretty cool. Yes, no, maybe. If you're curious about that at all, if you're into fractal geometry, if you look at that thing and go, wow, that's pretty. If you took pre-calc with me, then you saw this already. But you know, polynomials like quadratics and other higher order polynomials, they have roots, numbers that make them zero. And sometimes those roots are non-real complex numbers, like, you know, your quadratic formula sometimes spits out stuff with i's in it. These pictures, this picture is the complex plane. So like the number 1 is right here. The number I is right up here. Over here would be the number, actually, I guess over here would be the number 1 plus I. This is the number -1. This is down here is the number -I. What this guy did, this researcher at UCR, he generated a bunch of random polynomials and then had a computer calculate their roots and then plotted all those roots in the complex plane. It's like this is the number 0 right in the middle. Along this line here, this is the real line. This is the number 1, this is the number -1, I, -I, and so on. Turns out when you plot all the roots for a bunch of polynomials, you get some really weird patterns, like really weird patterns, like these kind of fractals in here. These are called dragon fractals. They're well known. These sort of feather fractals are well known. And the fact that this shows up is very surprising. If you know anything about fractal geometry and how those fractals are normally created, seeing them show up here is fucking shocking. And if you find this at all pretty, which I tell you, I certainly do, there's a lot of really neat open research questions related to this, and it's totally accessible. You can work on this stuff after just learning a bit of pre-calculus. So I wanted to share it with you. The link is in the chat. If you find that at all cool, check out the page. And if you are genuinely inspired by that or want to play with this stuff at all, talk to me about the math team. The math team here at Santa Fe has been pretty quiet since COVID started, but we're starting to boot things back up. So you see I'm wearing a, I guess you can't see it right now, I'm wearing a shirt today from the Math Olympics. I forget what year it was 2019. Every year Santa Fe sends a team to the Math Olympics, and it's been canceled for the last 2 years, but next year in the spring we are doing it. So if you find mathematics enjoyable and you would like to train and solve some competition problems, maybe make some money, get some scholarships, make some cool connections, then the math team is a good way to start down that road. We also have an integration bee. I don't know, it's like a spelling bee, but with integrals that UF puts on every year. And Santa Fe, we used to send a team to that, and I would be happy to get a group back together. So if you enjoyed all the stuff we were doing with integrals, then maybe you want to be a part of our integration bee team. All right, that's enough of this. Let's get back to talking about series. So this is MAC2312 section 004, which is Calc 2. And today is the 25th of October, 2020. today, we'll talk about alternating series. And alternating series tests. So what is an alternating series? Again, let me remind you, all of our convergence tests except for the test for divergence. Greater than or equal to 0.
No tenemos una calco.
So far we've had any convergence tests where we can handle series that have some positive terms and some negative terms. I'm not including in this geometric series or telescoping series. Those really aren't tests, right? Those are just like, we have theorems that tell us what the series do. But like, you know, the integral test requires that the corresponding function be positive, which means that the terms of your series are positive. The two comparison tests, the direct comparison test, the far left side of that inequality is 0. So those terms have to be positive. And the limit comparison test says if sigma an and sigma bn are series of positive terms, then blah, blah, blah. So all of our convergence tests so far, except for the test for divergence, require the terms of the series to be greater than or equal to 0. Today, we'll play with lots of series where exactly half of the terms are positive and half are negative. And those will be arranged as like alternating, one positive, one negative, one positive, one negative, one positive. And that's what we mean by an alternating series. It turns out alternating series have a much easier time converging than series of positive terms. And that's kind of similar to what's going on with telescoping series, where like the next term sort of takes away a bit of the previous term. It's not a full collapse like you get with telescoping series, but it's kind of the same thing in feeling. I had a professor would say morally, it's the same sort of thing. So let me give you a definition. Oh, this section number, by the way, this is 11.5. All right, so let me give you the definition. An alternating series is a series where the terms change sign. Positive to negative each term. Right, so you have a positive term, then a negative term, then a positive term, then a negative term, then a positive term, then a negative term. These can be written in the form. There's a few ways. So the way we normally do this is we say there is a power of -1, like -1 to the n, times some positive terms. So the bn's here are all positive, and this guy blinks you back and forth from being positive to negative. So this would be -1 to the 0 times b0, which is positive b0, plus -1 to the 1 times b1, which is plus negative b1, so minus b1, plus -1 squared times b2, so plus b2. and then minus B3 and plus B4. You get the idea. It can also be written like this. There's actually a bunch of different ways you could write this. And equals 0 to infinity. Negative 1 to the n plus 1. Bn, which would be like negative B0 plus B1 minus B2 plus B3. Oh. So the idea here is that a power of -1, like -1 to the n, or -1 to the n plus 1, those, we studied those as sequences. Remember, we looked at the sequence -1 to the n. It just goes 1, -1, -1, -1. So this piece gives you the alternatingness, right? It's the -1 to the n or -1 to the n plus 1 that gives you the minus, plus, minus, plus pattern. And the bn's here, these are assumed to be non-negative because I actually want this term to be negative. And if B1 was itself negative, then negative B1 would be positive. Of course, these series don't need to start at 0. They could start at 1 or 2 or 3. And there are other things besides -1 to the n that can blink you back and forth between being positive and negative like that. I'll show you some examples, but this is the standard way of writing things. A quick example, alternating series. I showed you a few the other day. If I take sigma n from 1 to infinity, -1 to the n plus 1 over n. And I start writing out the terms. This is -1 squared, which is +1 over 1. So it starts out with 1 over 1. The next term would be -1. So it's n equals 2, -1 to the 3 over 2, minus 1/2. Plus -1 to the 4 is +1 over 3, minus 1 over 4, plus 1 over 5, minus 1 over 6, and so on. This is an alternating series. And I can write S in that form just by taking that power of -1 and moving it over a little bit. So I can write this as sigma n equals 1 to infinity, -1 to the n plus 1 times 1 over n. And just a little baby algebra inside here, right? And so this thing being upstairs is the same as having that thing over here and a 1 upstairs. So here, the bn's are just 1 over n. Everybody comfy with why this thing is an alternating series and why its bn's in this definition would be 1 over n? Okay, let me show you one more. Yeah.
No. Did you ask? No, I don't think so. Are
So
you?
the series
Probably.
sigma n
Okay.
from zero
Bye. Enjoy the day. Yeah.
n plus 1. This is also an alternating series. Here again, if I want to write this in that kind of standard form for an alternating series where I've got the alternating piece times a positive piece. I would write this as S equals sigma n from 0 to infinity, negative 1 to the n times 1 over 2n plus 1. So here, the dn will be 1 over 2n plus 1. All right, nothing crazy, right? Just how to write these things, how to recognize them when you see them. I'm going to show you two more examples. Clear on why the bn's for the first series are 1 over n and why the bn's for the second series are 1 over 2n plus 1. Any questions about that?
I had a quick question. What we're reviewing here with that second example is determining whether it's an alternating series depending on the bn being greater than or equal to 0, correct?
Yeah, that's the idea. I'm asking, can I write this series in this form or this form where the bn's are positive, non-negative? Yeah.
Okay, so it's just a rewriting of the series.
Yep. Yeah, really not doing anything with them here besides verifying that they can be written in this form.
Okay, thank you.
So let me ask, are any of the following alternatives? Let me do Q. So for Q, let's look at sigma n from 1 to infinity. -1 to 2n plus 1 over squared. For R, look at sigma n from 0 to infinity cos n pi over 2 to the n. For S, let's look at sigma n from 1 to infinity, -1 to the 2n over n factorial. And for T, let's look at sigma n from 0 to infinity, -1 to the n over 2n plus 1 factorial times n. All right. So for each one of these, I just want to answer, is it an alternating series? And if it is, can we write it in that form, sigma -1 to the n times bn, where the bn's are non-negative? And some of these might surprise you. Now the trick, as you might have guessed, is going to be to just write out the first few terms, right? If I write out the first few terms of each series, I should be able to see whether it's blinking back and forth between positive and negative. So for the series Q, if I plug in n equals 1, I get -1 to the 2 times 1 plus 1 is -1 cubed over 1 squared. And then the next term would be -1 to the 2 times 2 plus 1 is -1 to the 5 over 2 squared. And then the next term would be -1 to the 2 times 3 plus 1 is 6 plus 1 is -1 to the 7 over 3 squared, and so on. Now, -1 cubed is -1. So this first piece is just -1, right? -1 over 1 squared. The next piece, -1 to the 5, is also -1. So this is -1 over 2 squared, or -1/4. The next term after that is -1 to the 7, and -1 to the 7 is also -1. So this would be -1/9. So is this an alternating series?
No?
No, it's not. All right, very good. This is not alternating. So kind of the lesson here is that just because you have a power of -1 doesn't automatically mean you're alternating. Why did this series not end up alternating? What is it about this thing that made it all the terms negative? About these numerators.
They were all to an odd power.
Good. The power of -1 here is always odd, right? 2n plus 1 is always going to spit out an odd number for any integer n. And an odd power of -1 is always going to be -1. So the kind of thing that makes -1 to the n blink back and forth is that n itself goes from even to odd, even to odd, even to odd. So 2n plus 1 doesn't do that. It's always odd. So -1 to an odd power is always just going to be -1. Could I rewrite this series in a way that is a little bit less opaque? I'm going to come down here. So Q is not alternating. All the terms are negative. Since -1 to the 2n plus 1 is always -1 for all n, for all integers n. In fact, I can rewrite Q. If -1 to the 2n plus 1 is always -1, then this series is really sigma n from 1 to infinity, -1 over n squared, which is negative sigma n from 1 to infinity, 1 over n squared. Now, just for fun, let me see if you've been paying attention. Does this series Q converge or diverge? Yeah, Frank got it in the chat. This series converges. The -1 to the 2n plus 1 is just -1. That's a constant, so I can pop that out of the series. I get negative sigma 1 over n squared. And this guy, without the negative, that's a p series, p equal to 2. 2 is bigger than 1. So this is a convergent series, but it's not alternating. All right, let's look at R. And I'm going to go ahead and just come down here because I want to have plenty of space. So the series R is sigma n from 0 to infinity cosine of n pi over 2 to the n. And I just write out the first few terms. So when n is 0, you get cosine of 0 over 2 to the 0 plus. When n is 1, you get cosine of pi over 2 to the 1 plus. When n is 2, you get cosine of 2 pi over 2 squared plus. When n is 3, you get cosine of 3 pi over 2 to the 3, and so on. What is the cosine of 0?
1.
Good, this is 1. So this is 1 over 2 to the 0 plus. What is the cosine of pi? Not your unit circle. Yeah, the cosine of pi is -1. Thank you, Coburn. So this is plus -1 over 2 to the 1 plus. What's the cosine of 2 pi? +1. Good. So this is 1 over 2 squared plus the cosine of 3 pi. -1. Very good. Thank you, Richard. So it's -1 over 2 cubed, and so on. This is a 2 raised to the 3rd power. So this is 1/2. Sorry. So this is 1 minus 1/2 plus 1/4 minus 1/8 plus, and so on. This series is geometric. It's well hidden, but this cosine of n pi turns out to do the same thing that -1 to the n does. You can think of it as like running you around from those two extreme points on the unit circle. Cosine of n pi is taking you from 1 here to -1 here, and then back around. Right, and those 2 points on the unit circle are 1, 0, and -1, 0. So cos 0, cos 1, cos of 0, cos pi, cos 2 pi, cos 3 pi, cos 4 pi, cos 5 pi, just goes 1, -1, 1, -1, 1, -1, the same as -1 to the n. So this is alternating. It's also geometric. All right, this is the same as, I could rewrite this. That's R equals sigma n from 0 to infinity, -1 to the n over 2 to the n, which is the same as sigma n from 0 to infinity, -1/2 to the n. So the common ratio is R equals -1/2. And I'll not write any more about this, but if you have a geometric series with common ratio -1/2, is that series going to converge or diverge? Yeah, correct. It will converge. All right, this is I'll go ahead and write it. So the absolute value of R is the absolute value of -1/2 is 1/2, which is less than 1. So the series R converges. And we could even find its sum, right? Because we know everything there is to know about geometric series. But again, I'm not going to do that. We're just trying to figure out, are these things alternating series or not? The kind of take home here is that cos of n pi is actually equal to -1 to the n for all integers n, which is a pretty sneaky trick. Pretty sneaky trick, I think. Okay, 2 more. Sorry, so I didn't mute you guys by default today. If you know you've got noise in the background, I'll ask you to please mute. So my series S here, sigma n from 1 to infinity, -1 to the 2n over n factorial, without even writing it out. Do you think this is going to converge or diverge? I'm sorry, converge or diverge. Do you think this alternates or not?
I'll say it doesn't.
Yeah, that's correct. That's correct. Do you care to explain a little bit your thinking there, Enrique?
It's due to that the exponent on the numerator is going to be always even.
Perfect. Yeah, the power of -1 here, 2n, is always even, which means the terms here are actually going to be all positive, right? This is starting at 1, so this is -1 squared over 1 factorial plus -1 to the 4 over 2 factorial plus -1 to the 6 over 3 factorial plus -1 to the 8 over 4 factorial, and so on, which is just 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial. This is not alternating. And Enrique is exactly correct about why. It's because the power of -1 here is always even, and an even power of -1 is always just 1. Okay, last guy. -1 to the n, so here, t equals sigma n from 0 to infinity, -1 to the n over 2n plus 1 factorial times pi to the n. Okay. So if I start writing out the first few terms here, I will get -1 to the 0 over 1 factorial times pi to the 0. My next term would be -1 to the 1 over 3 factorial times pi to the 1. And then -1 squared over 5 factorial times pi squared. And then -1 cubed over 7 factorial times pi cubed, and so on. -1 to the 0 is 1. So this is pi to the 0 divided by 1 factorial is just 1. -1 to the 1 is -1. So this is minus pi over 3 factorial. -1 squared is positive. So this is plus pi squared over 5 factorial. -1 cubed is negative. So this is minus, so this is a 2 minus pi cubed over 7 factorial, and so on. So does this guy alternate?
Yes.
Yeah, this one does. This is alternating. And the BNs here would be what?
Is it pi to the power of n over 2n plus 1 factorial?
Very good. Now, believe it or not, down the road, we will be able to do quite a bit with series like this. I think the exact way I've written this, I can't tell you what the value of this series is, but if I were to change this power of pi here just a little bit, I would be able to not only tell you whether the series converges or diverges, but by using some neat facts about the function sine of x, I could tell you what the value of the series is. And we'll get to that. There's going to be lots of cool shit like that down the road. But for now, I just want to recognize, are these alternating or are they not? Okay. And now that I know how to tell when a series is an alternating series, it's time to discuss the alternating series test, which is a test that applies only to alternating series. So if you're given a series and you think it might be an alternating series, you should check. And if it is indeed an alternating series, you can apply the following test. So this is our next convergence test. That's called the alternating series test. This says if S is an alternating series with positive parts Bn, then S will converge provided two things are true. Now this is not an if and only if. right? This gives a sufficient criterion for the series to converge. It's possible for a test to not, or for a series to not satisfy these conditions and still converge. But if these things are true, then the series will converge. First thing, the sequence Bn has to be decreasing. I'm going to ask you to leave some space under this because I'm going to give you a couple different ways to show that a sequence is decreasing. And the limit as n goes to infinity of the Bn's is 0. So this is kind of startling. This is almost like a partial converse to the test for divergence. How do you show that a sequence Bn is decreasing? You've got two options. You can either show that the derivative Bn prime is negative, or you can show that Bn plus 1 is less than or equal to Bn for all n. And as you go through the homework and you click on the little help me with this shit things in WebAssign, they're most often going to do this. But it's not sufficient to check this for 1 or 2 values of n. You really do need to show that this inequality is true for all values of n. And the same is true for the derivative. This one is generally not that hard, right? You take the derivative, and at worst, you make a little number line, show the derivative is positive and negative. But this inequality work can be a little tricky, and a lot of people mess themselves up and get to thinking that, oh, if I show the first few terms have this pattern, then the whole sequence must have this pattern. That's not true. So if you're going to show me that the Bn's are decreasing, these are your two options. If you elect to go for the second one, the inequality, you really do need to verify that that inequality is always true, or at least from some point on. But it is not sufficient to just check 1 or 2 terms. I think WebAssign does sometimes in their little help me solve this stuff, just check 1 or 2 terms and go, okay, good. It's bullshit, right? Please don't do that. The startling thing here is that this is a really weak criterion. Now remember last Friday, we talked about the intuition behind series converging. And we said that, yeah, we do need the terms to go to 0. That's necessary, but it's far from sufficient, right? In general, having the terms go to 0 does not guarantee your series converges. The 1 over n series is a good counterexample. If that series happens to be an alternating series, though, if that series is an alternating series, and the terms go monotonically to 0, that's what this decreasing means monotonically, like constantly decreasing, that is enough. So somehow alternating series have a much easier time converging than series of positive terms. And I'd like to try and explain that reasoning for you. And the best way to do that is with a little proof. All right, so this is one of the few convergence tests. Well, it's not. I'm going to show you a little proof here, right? We offered a little proof of the limit comparison test also. Try and convince you this is a true statement. So what I'm going to do is I'm going to give myself a sort of generic alternating series. Say, let S be sigma n from 0 to infinity, -1 to the n, Bn be an alternating series. And suppose that the Bn's are decreasing with lim n to infinity Bn equal to 0. So I'm going to assume that I have an alternating series of the type that this test says should converge. if I want to prove that a series converges, I've got a few choices. I could either employ one of my other convergence tests, or I can work with the partial sums. None of my other convergence tests can be used here because this isn't a series with positive terms. So the only game in town is to work with the partial sum. The capital N partial sum for S is S sub capital N equals sigma n from 0 to capital N, -1 to the little n, b sub little n. So S0 is just B0. S1 is B0 minus B1. S2 is B0 minus B1 plus B2. S3 is B0 minus B1 plus B2 minus B3, and so on. And I'll write one more. It's 4 would be B0 minus B1 plus B2 minus B3 plus B4. What I'm going to do now, I'm going to say where if the BNs are decreasing, then B0 is bigger than B1, is bigger than B2, is bigger than B3, is bigger than B4, and so on. And the Bn are, of course, positive with lim n to infinity, Bn equals 0. So the B's themselves are getting smaller and smaller and smaller and smaller, and they're going towards 0. So in chat, Richard asks an interesting question. Is it because it goes towards a line? So I like the question. I want to interject a few comments. Be careful with the pronoun it. So when we say the word it, usually there's some implied noun behind that. And by it, we might mean the BNs, we might mean the series S, we might mean the partial sum Sn. So be careful using the word it. Always specify what specific noun you're talking about, because on any one of these problems, there's a bunch of things that could be the it. It's true that the limit of the BNs is 0. So the graph of the sequence Bn will be getting closer and closer and closer to 0, right? But that's not what does it for us. That's not what makes this series converge. The trick is going to be to look at the partial sums, and the partial sums will be getting closer and closer and closer to some specific value. But the reasoning is a little bit tricky to see. So what I'm going to do is draw a number line for you, and I'm going to plot the first few partial sums on that number line. Show you what I mean here. All right. So the first partial sum, or the 0th partial sum, if you like, B0, is just that one number. That one number is positive, and it's the biggest of all the B's. So let me put it over here. And that B0 is S0. Now, if I want to go from the 0th partial sum to the first partial sum, that's just B0 minus B1. And B1 itself is positive. So I'm subtracting something positive from B0, which is S0. So that means I'm going to move to the left. And the amount I'm going to move to the left is B1. And that will get me to S1. Because S1 is B0 minus B1. Now here's the cool part. As I go from S1 to S2, S2 has the same first two terms as S1, but then we're adding B2. And because the BNs are getting smaller and smaller and smaller, we're going to go to the right because we're adding B2, but we're not going to go past this, right? The distance here, the distance from here to here is B1. I subtracted B1. And like I said, to go from S1 to S2, I'm going to go back to the right because we're adding something positive. But the thing I'm adding has to be smaller than the thing I just subtracted because the BNs are assumed to be decreasing. So right here could be S2. And the big deal is that S2, this thing, has to be to the left of S0. This distance right here is B1. And to go from S1 to S2, I'm walking back to the right because I'm adding B2. And because B2 is smaller than B1, I'm going to walk a smaller distance back to the right. Does everybody understand why S2 is not over here somewhere? It has to be over here somewhere. Okay, now how do I go from S2 to S3? Well, here's S2, here's S3. The only difference between S2 and S3 is that we've got a minus B3. So that means I'm walking back to the left. I'm subtracting something positive. That takes me to the left. But because B3 has to be smaller than B2, I'm going to go back this way, but no further than this. I'm going to go back a smaller distance than this. So let me put some little tags here to help us keep track of where we're at. Extend this all the way over here. Now I'm going to walk back to the left, but it has to be a smaller amount than I just walked to the right. Say something like this, minus B3. And that means that this guy has to be S3. And S3 is necessarily stuck between S1 and S2. So you go S0, S1, S2, S3, and you start to see the pattern. S4 is going to walk back. Yeah, so why a smaller amount? Because the BNs are decreasing. Remember, those were our two assumptions for this series. The alternating series test says that your series will converge if the BNs are decreasing and have limit 0. So at the outset, I assume that I have an alternating series where the BNs are decreasing and the limit of the BNs is 0. So it's the decreasing nature of the BNs that guarantee we're walking less each time. So my next stop would be S4. To get from S3 to S4, the only difference is we're going to add B4, right? Here's S3, here's S4. The only difference is S4 has a plus B4. So to go from S3 to S4, I'm going to walk back to the right, but I'm going to walk back less than I just walked the other direction. So this would be plus B4. And that will get me to S4. So what do you notice about these S's? Just look at the top number line here. What do we notice about these guys? S0, S1, S2, S3, S4. They got to be coming in towards some point here because they're nested. right? These S's. Yeah, exactly. They're getting closer together. Now, if the limit of the BNs was not 0, then eventually I would get to a point here where I just toggle back and forth between like here and here, and then just bounce back and forth between those same 2 points. If the limit of the SN or the limit of the BNs was like 1, then I would bounce back and forth between here, 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 where this distance is always 1. So let's make some observations. These appear to be nesting. Since the BNs are decreasing, the SN are nesting is the word. Coming closer and closer to some point between S0 and S1. And what's more, because the limit as n goes to infinity of the BNs is 0, these arrows are going to get shorter and shorter, approaching 0 in length. As cap n goes to infinity. So we got to be marching inward here. And we got to be marching inward towards S, which is the full sum of the series. Yeah, so it's true that the graph of the ANs here would look like a damped harmonic oscillator. They're bouncing back and forth and getting smaller and smaller and smaller. The idea is that the partial sum of those is also bouncing back and forth and getting closer and closer and closer to some number S. So your textbook has a picture here that's a little better than I can draw by hand. Let's see. There you go. So you see 0 out to S1, back to S2, S3, S4, S5, S6, and we got to keep coming in like this because the purple arrows here have to shrink down to length 0. That's the statement that the limit of the BNs is 0. We have to eventually arrive at some middle value. And what guarantees this nesting is that the BNs are decreasing. So if you have these things nesting and eventually the distance from one to the next goes to 0, then this sequence of partial sums has to converge. So what's more, because the BN 0, the arrow's lengthen to 0, hence the SN have to pile up on some particular value. I.e., the sequence of partial sums has a limit. And that is exactly what it means by definition. Means the series S must converge. And that's it, that's the proof. There's a relationship here between damped harmonic oscillators, but it's not as cut and dry as we might like. So this would be kind of like the integral of e to the negative x cos pi x or something like that, but but not necessarily. It's like cos pi x times your whatever the Bn function would be. All right. So the proof is nice, right? The pictures are nice, but we need to learn how to work with the test. So understanding the proof will help you understand why it's easier for a alternating series to converge than it is for a series of positive terms. If you have a series of positive terms, then all of these arrows point to the right. So the arrows have to shrink down a lot faster in order for the series to converge. With an alternating series, every other arrow points the other way. So as long as the length of the arrows goes to 0, the series will converge. Think about why this doesn't work for a series of positive terms. Remember what I said, for a series of positive terms, all the arrows would point to the right. So let's take some of those alternating series we looked at the start of the class and apply the alternating series test. We said earlier that this is an alternating series, right? This is like 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 and so on. This is an alternating series. And the BNs here we identified earlier are 1/n. So I can use my alternating series test. You always want to tell your reader what test you're using. And there's the two things we have to check. Check that the BNs, which are 1/n, are decreasing. And lim n to infinity, Bn equals 0. Decreasing. Well, this is one where we could use either of those two tools pretty easily. So the Bn plus 1s, if I take B sub n plus 1, that's 1/n plus 1. And 1/n plus 1 is smaller than 1/n, which is Bn. Why? Because the denominator is larger. Right? 1/3 is smaller than 1/2. 1/4 is smaller than 1/3. So yes, the Bn are decreasing. The sequence Bn is decreasing. The alternate approach here would be to look at the derivative of Bn. Right? And the derivative of 1/n is negative 1/n squared. So I can show you really quick. I could say that Bn primed is 1/n primed is negative 1/n squared, which is negative for all n equal 1, 2, 3, and so on. So by this argument, the Bn are decreasing. Either one is fine. I think the inequality is nice to use when it's obvious, but if the inequality isn't obvious, then you should probably use the derivative. Is the limit of the Bn 0? Yeah. Lim n to infinity of the Bn is lim n to infinity of 1 over n is 1 over infinity, which is 0. So yes, we are decreasing, and yes, the limit is 0. Plus, by the alternating series test, which I will abbreviate AST, the series S equals sigma n from 1 to infinity, negative 1 to the n plus 1 over n must converge. Without the negative 1 to the n plus 1, this series diverges. Right? If you take away the alternatingness and you just look at sigma 1 over n, that's the harmonic series, which diverges. So making that series alternate changes it from a divergent series to a convergent series, which is pretty cool. There's a special name for series like that. They're called conditionally convergent. And I'll talk about that more later. There's a name for this series. It's called the alternating harmonic series. Right, so the regular 1 over n series is called the harmonic series. This is called the alternating harmonic series. Okay. Questions on this use of the alternating series test? Okay. Let me grab another problem or two from your book. Examples in here, yeah, the alternating harmonic series is a classic. We can do this. N squared over n cubed plus 1. So let's investigate the series. Sigma n from 1 to infinity, negative 1 to the n plus 1 times n squared over n cubed plus 1. So certainly this is an alternating series. Right? If you write out the first few terms, when n is 1, you have negative 1 squared, which is 1, times 1 squared over 1 cubed plus 1, which is 1 half. When n is 2, you have negative 1 cubed, which is negative 1, so that's minus 2 squared is 4. 2 cubed is 8, so that's 8 plus 1, which is 9. And then the next term would have a negative 1 to the 4. This is the n equals 3 term. So that's 3 squared, which is 9, over 3 cubed plus 1. 3 cubed is 27, so that's 28. And then the next term would be minus 4 squared is 16, over 4 cubed is 64 plus 1 is 65. And it goes on like this. So indeed, looking at it, this is an alternating series, right? The terms are positive, negative, positive, negative. This is an alternating series. So we use the alternating series test. And I'd like to point out that we cannot use any other test on this or the previous series, because all those other tests require that your series only have positive terms. Yeah, so to conclude that the series is alternating, you just need to recognize that the power of -1 here goes back and forth from even to odd. So if this was just even or just odd, then the series wouldn't alternate. But you'll see me writing out the first few terms of the series a lot. It's a really good idea. It kind of gives you a feel for what the terms of the series look like, and that can be very helpful for coming up with comparisons or doing all the other stuff that we like to do with series. So even though you can look at this and say, yeah, this piece will make it alternate because this stuff is definitely positive, and jump straight to your alternating series test, I always recommend writing out the first few terms of the series, no matter what you're going to do with it, because it just really helps you get a feel for what's going on with the series. I can kind of see how quickly the denominator is growing compared to the numerator. That can help me kind of guess at my limit if I think that limit's going to be tough, and sometimes having a guess can really help. It can also help you see things that are somewhat disguised. Like, some of the series we've looked at happen to be geometric, even though they were also alternating. And it's easier to work, with the theorem on geometric series than it is the alternating series test. So yes, you can look at this right away and see that it's alternating, but I still like writing out a few terms. All right, there's two things we need to check. Are the BNs decreasing? And is the limit of the BN 0? So first, let me just get in here and work with the decreasing nature of the BNs. So the BNs here are n squared over n cubed plus 1. And this time, good luck showing the inequality. Showing that Bn plus 1 is less than or equal to Bn algebraically is hard. Right, if I replace the n's by n plus 1s, the top becomes n squared plus 2n plus 1. The bottom becomes n cubed plus 3n squared plus 3n plus 2. And it's very hard to show that that thing is smaller than this thing. Quite hard, I think. So verifying this algebraic inequality is tricky. Better to use the derivative. So let's look at the derivative of my BNs. This will be a quotient rule derivative. It's still a bit of work, but I promise you it's easier than trying to prove that inequality. Remember what your quotient rule says, bottom times the derivative of the top. So that's n cubed plus 1 times 2n minus the top, which is n squared times the derivative of the bottom, which is 3n squared, all over the square of the bottom. Now, this bottom is always positive, so I'm not terribly worried about him. I do need to clean up the top to figure out what's going on. So I have n cubed times 2n, which is 2n to the 4. Uh, 1 times 2n, so that's plus 2n, minus 3n to the 4. All of this is over n cubed plus 1 squared. So I can continue over here. If I combine my like terms, 2n to the 4 minus 3n to the 4 is negative n to the 4. And I have a plus 2n. And all of this is over n cubed plus 1 squared. Now remember what I'm trying to check. I'm trying to ask, is this thing negative? Since the bottom, n cubed plus 1 squared, is always positive, it's a square. it suffices to show, to check when the top is negative. Plus 2, sorry. Okay. So negative n to the 4 plus 2n, if I factor out a negative n, is n cubed plus 2 left. So this thing is capable of changing signs at a few different places. Let me say it like this. So this can change sign when n equals 0 or n cubed plus 2 equals 0. Now there are 3 solutions to that second equation, n cubed plus 2 equals 0. But 2 of them are non-real complex numbers. You can get them all by using your sum of cubes formula, but I'm only interested in real numbers here. So this would be n cubed equals negative 2, which would mean n is the cube root of negative 2, which is negative cube root of 2. Right? Cube roots and negatives, they play nice.
Professor, wouldn't it be n cubed minus 2?
Oh shit. Yeah, you're right. You're absolutely right. Yep, this should be a minus. This should be a minus, which makes this a plus, which makes this positive and positive. Yes, thank you. Thank you. Thank you. Yeah, sorry, we factored out a negative n, right? So this became positive, this becomes negative. Thank you, thank you, thank you. Okay, so this thing can change sign when n is 0 or the positive cube root of 2. So I make a number line. You guys remember how to do this from Calc 1? You're just checking where this thing is increasing and decreasing. I've got 0 and the cube root of 2. And I can test a point from each region. If you plug something into the left of 0, like negative 1, you would get negative 1 to the 4 plus 2 times negative 1. Right? Negative 1 minus 2 is negative. So if I test n equals negative 1, you get a negative in here. The root or critical number at 0 is coming from this odd multiplicity factor. So I will blink back to being positive here. Or you could test something between those two. It really doesn't matter. And then you can test something to the right of cube root of 2. You could test something like n equals 2 itself. Right? 2 is definitely bigger than the cube root of 2. If you plug 2 in here, you get negative 2 to the 4, which is negative 16, plus 2 times 2, which is positive 4. So negative 16 plus 4 is negative 12. So we are negative here. And this is the sign of Bn primed. Therefore, the Bn's are decreasing for all n's greater than the cube root of 2. And remember, n is supposed to only take on integer values. The cube root of 2 is like 1.6 or something. Right? Let me check. Smaller than that. Yeah, 0.3, sorry. Oh, wait, hang on. That's just giving me 1/3. Yeah, 1.25. Sorry. Okay. So for any n larger than 1.25, the Bn's are decreasing. In other words, this thing isn't always decreasing. but it is decreasing from 2 on, which is good enough, right? We don't need this thing to be decreasing at every single value of n, but as long as it's decreasing from some point onward, we are good. So the BNs here are eventually decreasing. They start to decrease at 2 and they stay decreasing thereafter. So we are good with the decreasing. The only other thing we need to check is that the limit of the BNs is 0. And here, that limit is also a little tricky. It's the limit as n goes to infinity of n squared over n cubed plus 1. And if you just go plugging in infinity, the top and bottom both appear to be infinity. So you could use L'Hopital's rule, but you're going to need to use it a couple times. I don't, at least once. L'Hopital's rule is okay. We'll do that. That's probably what most people would do anyway. So this is an indeterminate ratio. So if I apply L'Hopital's rule, I get lim n to infinity. Yeah, one L'Hopital will do it. Upstairs you get 2n, downstairs you get 3n squared. And that limit, this is lim n to infinity, 2 over 3n. So that is 2 over infinity, which is 0. So the BNs are decreasing. Takes them just a second to decrease, but then they decrease from thereafter. And the limit of the BNs is 0. Therefore, by AST, series S equals sigma n from 1 to infinity, -1 to the n plus 1, n squared over n cubed plus 1 converges. Right? Because those two requirements are met. So this is the alternating series test. It's really not that hard to work with. You have to show that the BNs are decreasing and show that the limit of the BNs is 0. And as long as those two things are true, your series, your alternating series, converges. One last comment before we go. The alternating series test, I guess two of them. I know it sounds silly to say, but it only works for alternating series. Don't try to use the alternating series test on a series which doesn't alternate. Can't do that. The other one, and this is maybe the more important one, the alternating series test can never, ever tell you that a series diverges. Just like the test for divergence can never tell you that a series converges. All right, so the alternating series test says if these two things are true, then your series converges. But nowhere does it say if these things aren't true, then your series diverges. That's not the case. It's a one-way street, and it only applies to alternating series. It's true that for the upcoming test, I do not expect you to sum most series. I don't expect you to tell me the value of most series. Now, there are some exceptions, right? Telescoping series, geometric series, those you do need to be able to find the value of. But for these like alternating series, for most of the things you're going to apply a comparison test to, for the vast majority of the series we work with in general, no. You're not expected to find the value of the series. I just wanted to know whether the series converges or diverges. The only exceptions are geometric series and telescoping series. Those guys you should be able to find the value of. All right, I think we are out of time. I got to go ahead and pull the plug here for the day. There's going to be a fresh homework up for you guys a little bit later. I haven't published it yet, but it will be up a little later in the day. I do have an office hour today from 1 to 2 p.m. So if you want to come chat about some stuff, it's a great time to do it. If you have any other questions, can't come to the office hour, Discord is good, Canvas is good. Y'all know the drill at this point. Please make sure you're keeping up with the homework. If you need more time on anything from last week, submit an extension request. I'll be blasting through those around 1 p.m. today. That's it. So I will see you guys on Wednesday.